Hi, I'm Wade Martinson, Technical Director for Cargill Process Optimizers. I'd like to talk about food process modeling. This capability, developed by Cargill, has delivered hundreds of millions of dollars in annual value over the past 15 years. Cargill Process Optimizers makes this a key part of its offering to select Cargill customers. Let's see what it's all about. Cargill is constantly on the lookout for ways to improve process efficiency. We operate in very low-margin industries. Processing efficiency is everything to us. We looked around and we've seen how other industries like petrochemical, fine chemical, pharmaceuticals have realized significant value from process modeling. We looked around, however, and found that the existing tools that were available did not translate to the agri-food space. This is for a couple of reasons. First of all, our materials are very different. Where in petrochemical, you know the molecular description of every material you're dealing with. Here we deal with things like wheat flour or soybean meal or biomass that can change from year to year, from geography to geography, and can't be described by a single molecule. Second, our equipment, our processes are unique. We use unit operations that just aren't found in a traditional oil refinery. So we made the investment ourselves to develop our own very powerful process modeling capability. And this capability is suited to our materials, our processes. So how does this capability deliver value? Well, at its most basic level, what we do is combine fundamental knowledge of our process with real data. We wrap this into a framework that gives us quantitative insight into process performance. This is the process model. I'm not talking about a statistical model with correlations. These are models built on fundamental physics of the world we live in. Mass balances, energy balances, transport equations, that sort of thing. These models let us extrapolate with confidence. They help us reconcile the data that we pulled in from real instruments that have their own sources of error. When we've built this framework, it gives us a tool to rapidly understand process improvement ideas and what their true impact might be. It captures the impact across the entire process. Often, let's take the example of heat reclaim. A second heat recovery project will return value, but it will partially suppress the value of the first heat reclaim project that we did. There's less heat available for that first project to reclaim. By capturing the entire value over the whole process, we get a better idea of the payback on investments we're considering. Really, it boils down to this. We can identify and execute the right projects, find the ones that give us step change process improvement. All right, let's take a look at how these modeling tools can help optimize a process. What you see behind me on the screen is a simplified process. It's for demo purposes only. It's not a real process, but it helps to illustrate a lot of the principles and the ways we use process modeling to improve process performance. The overview of the process is as follows. We take a raw material, slurry it up with water, preheat it, pass it to a reactor. In this reactor, some of the raw material transforms into our soluble product. There's also a side reaction which consumes some of our product and converts it to an insoluble byproduct. After some heat recovery, we're able to separate our product, which is soluble, from our unused raw material and our byproduct, which are insoluble, in a simple filter. So that's what we see here. The filter cake, which is mostly unused raw material and byproduct, is still wet, and that held up liquid contains product. To increase yield, then we pass that to a second recovery filter. In this filter, we just wash the cake with water. Like I said, this improves yield. So the clarified liquor from the first and second filters passes to an evaporator feed tank. After preheating, we need to evaporate this. We concentrate it up to final product concentration, cool it for storage, and put it in the product tank. Like I mentioned earlier, this type of model is not just simply a polynomial fit to data. This is built from mass energy balances, physical property calculations, transport equations, that sort of thing. Gives us a couple things. One, it lets us see things that are not measured. You can see that I can click into any stream or any block here, I can get compositions, flows, etc. Really, this is just closing mass balances, but it's very nice for reconciling your data, coming up with one consistent set of information from which to make decisions about your process. We can layer on calculations as we wish. In this case, we've built some other calculations, I've summarized them in a table here, related to the economics of the process. So given current product sale price, raw material cost, cost for natural gas, say for a boiler, other utility costs, we can calculate things related to the economic performance of the process. It's kind of an eye chart, certainly not visible in this demo, only slightly better, but I will switch over to an Excel spreadsheet I've prepared. We can copy and paste over that. Alright, so we've already talked through how we can build a process model, reconciling the data that you have, and using it to calculate and infer things that aren't directly measured. We've added on economic calculations, and we're going to take those and use them to evaluate some process improvement ideas. The first one that you can see is a trade-off that's built right into the process. In the second filter, we're washing additional product off of the cake from the first filter. This is a diminishing return situation, however. As you use more and more water, incrementally less and less additional product is recovered. All that water has to be evaporated, and that takes steam. That takes gas or coal, biomass. Regardless, it has a cost associated with it that just keeps climbing as you use more and more water. Now, when the process was built, there was a certain set of costs for the raw materials and fuels that you use, a certain cost for the steel, the capital to build the process, and a certain sale price for the product. So at that time, there was a certain optimal wash ratio. That may have been a long time ago. Things may have changed. It may be worth revisiting that ratio between the amount of water that you use and amount of cake that you're washing. So let's take a look. I'm going to switch back to the economic summary table that I built. We see right now we're at about $20,000 or euros per year generated from this facility. Let's see what kind of impact we can have if we change that wash ratio. Right now it's 2 to 1. What if we made it 1 to 1? Let's take a look. Click of a button, we run that through the model. I'm going to take this over to Excel. I've formatted Excel to show things that improve with green, things that get worse in red. We see at the top, yes, it could be very worthwhile incremental value of about $210,000 per year from changing the wash ratio down from 2 to 1. We look at what gets changed. Our first red here is on yield. We are giving up a little yield. We're using less wash water. However, in this case, we spend much less on steam, and the savings on steam is not, it more than outweighs the loss in yield, the small incremental loss in yield. So let's go back. Why not, since this is math at this point, it's a process model, let's use it. Let's make it an optimization and find the best wash ratio, the one that maximizes the profit that we can make here. And we see, actually we can go even farther. Instead of 2 to 1, if we go nearly to 1 to 2, flip it around, we've improved things even more. I'm going to paste it in here. Then I'm going to read it. I know this isn't viewable or not readable from the screen. Incremental value is about $250,000 per year. That is definitely worth exploring. Now, this isn't to say that just because the model says so, run out and do it. But it says, hey, is it interesting for $250,000 to take a closer look at how much water is used on that recovery filter? Do we need to do a management of change? Do we need to dig into this further or not? If it had been $4, we'd probably say forget about it. But $250,000, that's significant. We might want to pursue that further. Alright, we've used the model to examine how a change in the way we operate the recovery filter can have a significant effect on the overall economics of the process. We can use the model to look at more fundamental changes, however, actual changes to the layout, the equipment used, the configuration of the process itself. Let's take a look at how water is used in this process. We use a lot of water. We use it to slurry up the raw material, we use it to wash the filter cake, and then we have to evaporate it back off. What if we were able to reuse some of that water? So let's do the what if using the model. What if we were able to reuse that water that we've evaporated, take the condensate, and use it to slurry up new raw material? So I'm just going to reconnect that stream, easy in the model. And let's see how this influences the economics of our process. Again, we run the mass energy balances. This type of model lets us extrapolate, evaluate these kind of changes. Go to our economics table and compare it in Excel. So before we had achieved on paper about a $250,000 incremental improvement. It looks like by reusing condensate, even after we've optimized the wash water that we apply to the recovery filter, there's another $115,000 on the table for a total between the two projects of $375,000 potential increase in value. Again, this isn't to say that we just run out, call up a contractor and start making piping changes, but it says two things. One, there might be a significant amount of money on the table, again, if we were a little bit smarter about our water and tried to reuse some of it for our raw material slurry. Interestingly enough, it's often tough to justify water projects just on the basis of water savings. And here, that's not really the value. The model lets us dig in a little bit. What gets better? Our specific water use is this highlighted row. Sure, that's gotten a little bit better. Our spend on water has increased just incrementally about $300. That's all the savings, $300 per year. The savings comes in the energy that's contained in that water. That's where the value lies. You wouldn't justify this water project on the basis of water savings. You justify it on the basis of the energy that you save by reusing that hot condensate. So second point, again, it's what I mentioned before. It's not to say run out and do it, but is $115,000 worth exploring to add it to our project? It's definitely worth a look. The model also has captured interactions. Now we're talking about making two changes. We're talking about using the water differently and taking it from a different source. Those projects could have some interactions. You don't want to overpromise by looking at them individually, adding the value, and saying this is what we get when we do both. Using the model like this captures the interactions across the whole process and lets you make better choices about your final scope of project. So I don't want to talk too long here. Hopefully that gives you a feel for the many different ways that we can use a process model to help us really accelerate our process improvement efforts. We can look at changes in the way we operate. We can look at changes in the way the process is configured. We can look at additional things, startup and shutdown transition type behavior. We can even use this to get information used to examine schedule impacts on overall cost. This type of stuff and more. Extremely powerful tool. This is how Cargill has taken the next step in process performance. This is what Cargill Process Optimizers can bring to your facility.